Hello, Algebra 2 students. We are in lesson 35 today. We're going to talk about angles inside of polygons, and we're going to talk about angles outside of polygons. We're going to talk about inscribed quadrilaterals and fractional exponents. Sounds fun. Let's start with the angles inside of polygons. So we know that in a triangle, the interior degree measure of all of the angles is going to equal 180. So we use this as a basis for calculating the interior degree of measure of all polygons. And we do that by looking at a polygon and dividing it into triangles. And we even have a formula for that. So let's take a rectangle, for instance. We'll use it to start with just to show how we do it. We can take a rectangle and divide it into two triangles, right? So we know that this one is 180 and this one is 180. So we have 2 times 180. So the interior degree measure of a rectangle is going to be 360. And if you know rectangles, you know that this is 90, this is 90, this is 90, and this is 90. And 4 times 90 is indeed 360. So that proves true. So let's erase this for now. And let's dream up another polygon. Let's try this one, like a pentagon, all right? So there is a formula that we can use. It's n minus 2, let me get my pen, equals the number of triangles in a polygon. So let's test that theory first. We have 1, 2, 3, 4, 5 sides. So 5 minus 2 equals 3 triangles. So we should be able to say 3 times 180, which would give us, oh goodness, I can't do this in my head. I'm fighting a cold. My brain's not exactly clear. 3 times 180 is 540. So let's see if we have those 3 triangles in this polygon. You pick a vertex. Let's pick this one. We use the same one for all the triangles. So we go across. Here's one triangle. Here's another. All right, so we have it all divided into 3 triangles. So 180, 180, 180, 3 times 180. The interior degree measure of this entire polygon is going to be 540 degrees because we were able to do the 3 triangles. So far, so good. So we can use that from now on whenever we have a shape, a polygon, regardless of how many sides it is. We count the number of sides, we subtract 2, and then that's going to be the number of triangles we can make. We multiply that by 180, and that's the interior degree measure of the polygon. All right, so you're going to want to write down all of this example right here in your notes. And then we'll move on to talking about the exterior degree measure of any polygon. And the exterior degree measure of any polygon is going to equal 360. All right, and let me show you how we get that. Let me take a moment and draw a figure. All right, so here is a figure, and I've drawn an exterior angle in a counterclockwise motion. You can only do one exterior angle per corner or joining of sides, and that's what's going to equal 360. So as you walk around, or as you go around your polygon in whatever direction you're going, that's the direction you're going to draw your exterior angle. So let's start here. This is our beginning point. As we walk around and we go around it, we have an exterior angle here that's 75. As we continue around, we have 100 is a degree. Then we have 30, which is a degree. Then this exterior angle is 40. And then as we go around this corner, we have 115. So when we add all of those together, we get 0, 11, 12, 13, 14, 15, 16, carry 1. That's going to be 360 degrees. And this is where it might come in handy to have a protractor whenever you see this on a test. If there are no degree of measures given, you might need one for that. But for most of our tests, I believe you have enough information to draw the right conclusions and to find the answer. But know that it's only in one direction. It's not this angle and this angle. Okay? It's just in the direction, in one direction around. And it's just an extension of the direction you're moving in. All right, so let's clear this page and move on to a problem. All right, here's a problem we've been given. We have to find x and y. So in 35.1, we are being given all of these angles. So let's add these up and see what we have here. So we have 80 plus 40 plus 50 plus 65. That equals 235, okay? So 235 is what we know we have. And now we also have x degrees and x plus 55. That's all of our sides, and that should equal 360. So let's do a little squish and swim. So if we add 235 and 255, that gives us 290, and we have two x's. And that equals 360. So when we swim our little fish over here, we get that 2x is equal to 1. It's not 1. It's going to be 70. That's the difference. It's 70. All right, 360 minus 290 is 70. So when we divide 70 by 2, we get that x is equal to 35 degrees. So this becomes 35 degrees, and then we can sub this in to find this degree of measure. So 35 plus 55 is going to equal 90 degrees. So this is 90, which means that this is 90, because this is a straight angle, and if this is 90, then this is 90 as well, because that means this is perpendicular, and because 90 plus 90 is 180, and that is the degree measure of a straight angle. So that was number 35.1. That was not very difficult. You guys can do these in your sleep. I know you can. All of you have done well with these. So let's clear this one. And let's go on to, what are we talking about next? Yes, inscribed quadrilaterals. So I'm going to clear the page, and I'm going to draw you another figure, and then we'll work on it. So we remember with inscribed angles that the degree measure of an angle that goes all the way, we're going to pretend this goes all the way to the corner. I didn't draw it quite touching, but it's supposed to be. The degree measure of an inscribed angle that goes all the way to the other side is going to be twice that degree of measure for the arc that it bisects, or that it cuts. So from here to here, all that means is from here, which is this angle, So all the way around from here, all the way around from here, this arc is going to measure 2 times 80. So this degree of measure from here to here is going to be 160. Oh, and I forgot to put this. This is 50. This arc from here to here is 50. So if here to here, which is this degree of measure here, if that is the arc created by this 80-degree angle, then that means that z plus 50 should equal 160, because that's 2 times 80. Okay? So remember, the arc that the angle creates is double the angle of measure when the angle goes all the way to the other side of the circle. So z must be equal to 110 degrees. So now we know what this is. This is 110, and this is 50. So we just found z. Now let's see if we can find x and y. All right, so if this is 50, and this is 75, right? Then that means from here all the way around to here has got to be 2 times 75. So 2 times 75 is going to equal 150. And if this is 50, we're going to take 50 out of it. So that means that this sector must equal 100 degrees, right? All right, so this is getting easier and easier. Now we know that the total degree of the sectors of a circle is going to be 360. So if we start with 360 and we subtract 110, that's going to be 250, and we subtract 50. Then that's going to be 200, and if we subtract 100, then we're left with 100 for this remaining sector. That's what that has to be. All right, so now we know all of the sector measurements, which we should be able to determine the angle of each one of these. So if this is 100 and this is 110, that's the sectors for y. That's 210 divided by 2 equals 105. So y is 105 degrees. Okay? That equals y. So x is, we have 100 and 100, that's 200. 200 divided by 2, x is going to equal 100 degrees right here. And we can check that by, we know that the interior degree measure of a quadrilateral is going to be 360, so we just need to add it all up. So you have 75 plus 80 plus 100 plus 105. So let's say that's 10, carry 1, that's 6, carry 1, that's 360. So that comes out to the right degree of measure, which means we have found all the degrees that we need to find. Not too hard. You just have to remember what this means. Now, if this center, if the point of the angle is in the center of the circle, then it's equal. Then it would be, this would be 160, but because it goes all the way to the other side, it divides it by 2. So that's something to remember. And this is called an inscribed quadrilateral. Anything it's called inscribed, that means it's drawn inside of a circle. Okay? So let's clear this and let's go on to talk about fractional exponents. What in the world is a fractional exponent? All right, we are used to seeing our radicals like this. But we can also write that a different way. We can write the base, we can write the base's exponent, and then we can write the index of the radical. And that is what that would be. So again, this number is the base's exponent, and this is the index. So let me give you another illustration. If I were to say 10 to the 3/4, supposed to be 4, that would equal a 4 index and 10 to the 3rd, or 10 cubed. All right, you see how the numbers, where they come from? That's the 3 goes on top. That is the base's exponent, and the 4 is the index. If I were to give you this, it would be the same thing as if I wrote this, because it's understood that the index of a square root or of a radical is a 2 unless otherwise indicated. So let me show you something interesting about this. You have 2/2 as a fraction. What does that become? That becomes a 1, right? So literally this 2/2 is just 10, right? Because this reduces to 10/1, or to 2/2 reduces to 1. Well, if you put 10 squared in a square root symbol or in a radical, and your index is by default 2, guess what? 10 times 10, that's your 2 factors that you pull out, so the answer is just 10. So reducing the fraction when you have the opportunity to saves you a step. If I were to give you this, you could reduce that. You could reduce it to 3/4. Same thing. It would be the same result. And we can prove that. We can prove that it would be the same result. And we proved it here. Let's look at this one though. If we have 2 to the 6, right, with an index of 8, we're going to prove that it's the same as 2 to the 3 with a square root index, or with a radical index of 4. That's what we're saying, is that the reduction of the fraction would be the same. So let's pull up our trusty dusty calculator here, and we're going to put it in. We're going to do this the shortcut way. We're going to say 2 to the 6th is 64. To the square root with 8 is this 1.68179. We'll just write that part down. 1.6, hello, 1.681, 1.68, I cannot remember to save my life, 1.68179, and a bunch of other numbers. So let's do the same thing with this. 2 cubed to the square root of 4. Isn't that the same number? Oh my goodness, it's the same number. So yes, you can reduce. If you can reduce, treat it like you treat a fraction. It follows the exact same rules. So when you have 2/2, it's just the number here. This completely cancels and just becomes the number. If you can reduce this, why not do so that you have smaller numbers to work with? And it's much easier to calculate later. All right, so that is how you would use fractional exponents. So let's do a few. Let me clear this page. If you haven't finished writing your notes, then let's do so, pause and do so, and we'll move on. All right, let's look at 35.3. We have 4 to the negative 1 over 2. And be careful when you write this on your paper. Make sure you write it small enough and up above everything so that you see it is a power or an exponent, and it is not like 4.5, okay? You don't want to make the mistake of thinking it's a fraction. You want to remember that it is an exponent. So first of all, the base exponent is negative 1. So that means we need to flip this. So we put this as 1 over 4, and then there, you see how we did that? We got rid of the negative. And now we're going to put this into the radical symbol. So now it has its base, and we have our index of 2 because it's understood that this is 2 by default. So this equals 1/2. Right? Let's look at 35.4. Isn't that easy? It really is easy. You guys can do this in your sleep. I have every confidence that these are actually going to be fun for you. So we have negative 27 to the negative 1/3. So first of all, we flip it, right? So we have 1 over, and the denominator can never be negative, so we move it up to the fraction itself. 27 over 1/3. There it is. So now we put that in our index, or in our radical. I keep getting those mixed up. It's an indexed radical, that's why. So we put 27 in here to the power of 1, right? With a 3 index. And it's negative still. So 27 cubed, or to the index of 3, is going to be negative 1/3. Easy peasy. All right, let's do 35.5. We have 16 and, a different number, just like that. Now, when you have these two different numbers here, and this top number is not 1, there's 2 ways that you can do it. You can either take the base's exponent and calculate that first, or you can get the square root, or whatever this power index is, and do that first, and then do the exponent. So let's do it both ways. So let's come down this time. So let's do 16 cubed first. Let's pull up our calculator, and let's find that. 16, and if you have this symbol, which you should on a scientific calculator, you can just hit that. All right, that's 4096. So now we have 4096, and we've done this, so now it's to the power of 1 over 2. So that translates into this right here, right? And this, let's pull up our calculator, we still have this number. We can just hit this little button right here, and it tells us it's 64. So the answer is 64. Now we can do it the other way. So if we start here with 16 with a fractional exponent of 3 over 2, we could actually do this. We could say 16 1 over 2 and move the basis exponent to the outside. So we would be saying the square root of 16 cubed, so that would be 4 cubed. What is 4 cubed? Let's clear this. 4 cubed is 64. Same answer. This takes a few more steps and requires a little bit more thought, so it is entirely up to you which one you want to use. For me, I like to use them in the order they occur, so I can go ahead and scratch them out instead of doing the bottom first and then doing the top, because it just seems to go faster, fewer steps this way. But it's up to you, however you want to do it. So we have one more. Let's do 35.6. And we have a -8 to the -2 third power. So that's going to be, first we're going to flip it because we have a negative that we're going to flip, 1 and 8 squared over 3. So we got rid of the negative here, and we took the negative that was on the 8 and we put it on the fraction itself because we never have a negative in the denominator. All right, so now we're going to square the 8 and then get the cube root of that. So that's going to be default. Get the index from the bottom, and 8 times 8 is 64, right? So now we can just plug all that in the calculator. So look, we already have 64 in there. So we have 64, and then we have this little symbol here that says cube root. It's already built in. Bam! Cube root is 4. So the answer is going to be -1/4. How cool is that? Easy peasy, all done. And that's all we have for lesson 35. I will see you in lesson 36.